Computational Science Initiative, currently leading the high-performance computing group there. My background is in physics, specifically in lattice QCD research, but nowadays I am doing this high-performance computing in general with applications to high-energy physics, climate science, biology, etc. So I'll give you some flavors of the research I do at the end. But the topic today is exascale computing. So here's the outline of this talk. First, what is exascale computing and why do we care? And then I'll give you a bit of an overview of the US exascale computing project. But we can't talk about exascale computing without talking about the basics of high performance computing, and that's the main part of today's presentation. And then I'll also go over some basic examples of how we approach exascale computing in high energy physics, given my background. So that's what I will talk about. And then I'll give a quick summary. Right, so what is exascale computing and why? If you pay attention to computing news nowadays, you may have read the recent news about the world's first exascale supercomputer called Frontier, which is located at US DOE's Oak Ridge National Lab. So that's in Tennessee. And on the right-hand side, that's kind of a news clip of the headline of such a big deal. The world's first exascale supercomputer. And on the left-hand side is the newest top 500 list. And the first one, of course, is Frontier. If you don't know about this top 500 list, it's basically a list to rank the world's newest supercomputers. And the list is released twice a year. So they release a new list in the International Supercomputing Conference, IC, in June 2022. So that was just a few weeks ago. And they released another list in Supercomputing Conference in the US, which is usually in November. And you can see now Frontier is ranked #1. Fugaku was ranked #1 for the past few top 500 lists. And I'll talk about why this is so important in basically the remainder of the lecture. And if you look at this table, you can see that there's some system information. So like the maker of the system or the integrator, I should say. And then the architecture the system is composed of. So here you can see it has some CPU components, which are based on AMD's EPYC CPUs, and also a GPU component, which are based on the AMD MI250X GPUs. So you don't need to know the details of what these mean, but you just need to know that this system has both CPUs and GPUs. And Slingshot, this is the interconnect. So I'll also mention briefly why this is important. And then you see other numbers, like the total number of cores in the system, and then this RMX, which is the sustained performance that has been achieved using some benchmark. So I think for top 500, they use the impact benchmark. And then the peak performance, so which is the theoretical peak. I'll also go over this. And then the power. So power is a big issue in the exascale era because as the system gets larger and larger, we need to make sure that we have enough power to maintain the system, so to keep the system running without overheating, without drawing too much power, right? So into the site. Yeah, so I don't know what the preferred format for the summer school is, but I'm open to questions during. So if you have any questions, if the host can let me know, I'll be happy to answer them in real time. Or if you prefer to hold your questions to the end, that's also okay with me. Yeah, so what is exascale? So exascale refers to the ability for the computer to perform more than 1 exaflops per second. And 1 exaflop is 10 to the 18th floating point operations, right? And usually we use flops as a shorthand for floating point operations per second. So 1 exaflops is 10 to the 18th floating point operations per second. And to help you remember, the US has designated October 18th to be the exascale day. So there will be like some events focused on exascale computing on October 18th. So I think they may still do it this year. So you can pay attention to that. And why do we need so much computational power? I'm sure a lot of you attend the summer school because you are going to do research with some computational tools. And so because computing is ubiquitous in modern science and engineering, right? Numerical simulations need more and more computing power to get to higher resolutions and larger scales in your simulation to be able to more resemble the reality. And from the experimental side, we will be getting larger volumes of data coming in at a faster rate. And we want to be able to process this data quickly to facilitate decisions if you need to make some decisions based on the results of this data analysis, or you want to find new discoveries faster. And so here are just a few examples. So high energy physics, that's just to understand the fundamental building blocks of universe. And it has both theoretical side and experimental side, which I will cover later. And then because I'm from Brookhaven National Labs, we have a lot of these experimental facilities, such as X-ray light sources. So that we have this national synchrotron light sources, which basically uses X-ray to take images of very small samples, so to examine the very narrow structures of the samples, among other things. And you have instruments like this to take images, like X-ray images. And for this type of facilities, you can do both simulations, and also you want to do image processing after you have taken the images. And both of these can use up a lot of computational power if you want to do them quickly. And climate science research is also a big topic nowadays. And again, you have the simulation component and the data analysis component. So the Brookhaven lab also participates in several of the observational facilities to study the climate. And we also do multi-scale, multi-physics simulations, which involve very complex processes and can really benefit from large-scale computational power. And then there's also computational chemistry to understand, for example, the electronic structures of molecules. And this is also quite important for example, drug design and drug discovery. And so these kind of tools actually have played some important roles in COVID-19 related research for drugs and vaccines. So now, just a few slides to go over the US Exascale Computing project. So Exascale Computing sounds very exciting, but it also brings a lot of challenges. So in around 2016, US basically started this Exascale Computing project, which is a collaboration between US Department of Energy's Office of Science and NNSA. I can't remember what it's short for, but it's another agency in the Department of Energy. And the goal is to develop a complete ecosystem in support of exascale. So from software, hardware, facilities to training. And I quoted some statements on the Exascale Computing Project's website here. So Exascale projects.org. So if you go to that website, you will find a lot of useful information, very high level information, but you can see all the activities going on there. And the mission statement for US ECP project is developing exascale-ready applications and solutions that address many important important national interest targets, and also to create and deploy an expanded and vertically integrated software stack. So this focuses on applications, and the second point focuses on software. And the third point is deliver US HPC vendor technology advances and deploy ECP products, right? So this focuses on hardware, basically. Yeah, so this is kind of an overview of the US Exascale Computing Project. And if you look at the DOE's HPC roadmap from around 2012 to now and towards the exascale era, you'll notice that before, some of the supercomputers in the DOE's high performance computing center, so these are the so-called leadership class facilities. So they are very large scale supercomputers to support large scale simulations and data analysis. So in 2012, you see that there was still like IBM BlueGene-Q based systems, which are basically what we call homogeneous systems. So the whole system has one architecture, which is based on the multi-core, many-core BlueGene-Q chips, except Titan, which was based on so-called hybrid architecture. So it has a CPU component and a GPU component, which was based on NVIDIA's GPU. And as we move forward towards present day, the planned and the existing US supercomputing systems or leadership class supercomputers are all based on so-called hybrid architecture. So it has both CPU component and GPU component. So this is a high-level overview. I'll get into more details in the rest of the presentation. So bear with me at the moment. And on top of that, so before we only had the NVIDIA GPUs to basically serve as accelerators to the CPU, the host CPUs. Now we also have several different flavors of GPUs. So we have both AMD and Intel joining the race. That creates additional complexity to develop efficient software for exascale computers. And this slide was taken from Lori Daichin's presentation at NYSDS, last year's New York Scientific Data Summit. And Lori is the Deputy Director of the ECP project. Right, so as I just mentioned, yes, exascale computing is very exciting, but it also brings additional challenges. So the first one is because of the diverse architectures, right? So I already mentioned in the US, the current planned exascale computers will already feature different GPU accelerators. And if you look beyond the US and look at elsewhere in the world, exascale systems may be designed with, even more architectures. For example, Japan's exascale computer may be based on ARM architecture. So they already have this Fugaku supercomputer, which is ranked the second in the current top 500 list. And that's based on ARM's A64FX processor. So you don't need to know what this this name stands for. But you just need to know that this is also a kind of a homogeneous architecture. So one ARM processor has many identical cores. And so it doesn't have GPU accelerators. China's exascale computer, even though they haven't officially claimed to have an exascale computer, based on some scientific papers, for example, the one that just won the Gordon Bell Prize in supercomputing 2021, people are speculating that China already has exascale computers, and they are based on some homegrown architectures. And Europe is building its own exascale computer, I should say exascale computers, and we don't know what the architectures will be, but possibly with GPU accelerators. And another challenge is that even though we get a lot of computational power on each compute node, we have to connect different compute nodes into one big supercomputer through the interconnects. But the interconnects, they transfer data right, between different nodes. But the communication bandwidth that is enabled by these fabrics, it doesn't grow as fast as the computational power on the compute node. So this is why we will have fat nodes with very thin links. So if you need frequent communications between the different compute nodes for your algorithms to work, then the communication becomes a bottleneck. So in order to efficiently use these exascale computers, applications need to address both software and algorithm issues. So my talk today will focus on software issues. And I think foreign speakers will also present some algorithm issues from algorithms perspective. I know Dean Howard is going to talk about GPU computing and solvers, so he will probably touch upon these algorithm issues. So with the very high-level introduction out of the way, now let's go back to the basics. So what is high-performance computing? And what's challenging about it? But before I move to the next section, let me pause and see if you have any questions about what I just said. Okay.
Yeah, I do have a question
Okay.
actually.
Okay.
Yeah, so I'm of course I'm not at the level to understand what exascale computing is, but with the emergence of quantum computers, I was just wondering like how the speed compares, and also I understand that quantum computers usually work on different kinds of problems. So are there any like collaboration between exascale computing and quantum computing? Yeah, thank you.
That's a great question. Yes. So yeah, quantum computing is in a very exciting period, right? But right now, the scale of the present quantum computers is very small, right? In addition to that, they're very noisy. So there has been a lot of research in, from many different perspectives, from hardware perspective, from software algorithm and applications perspective, to see how we can scale up the quantum computers and to make good use of them, given the noisy nature. So I don't just my perspective, I don't think quantum computers are going to replace traditional high performance computers, but they may serve as, for example, accelerators to certain problems. As you correctly pointed out, quantum computers can solve certain classes of problems better than classical computers. And I think you have some lectures coming up on that. Yeah, so I think they are complementary, exascale computers and quantum computers, at least in the near future.
Thank you.
Yeah. Any other questions?
Dr. Lin, I had one as well.
Okay.
So for the HP systems that I've worked with or seen, they're all these Slurm-based queue systems with dozens or hundreds of concurrent users. As these new like top 500 systems come online, are they often single use or some predetermined slate of allocated jobs for whatever team they're working with? I'm just curious how often are these very large like exascale systems being used for single jobs versus some set of jobs across multiple different projects?
Yeah, so that's a very good question. And the answer is that all these big supercomputing systems are used by multiple users, multiple projects. And they usually have some predetermined allocations for these projects. So you have to apply for the computational time to use these systems. So in the US, if you want to use these leadership class computers or LCFs at Oak Ridge, Oregon, and also NERSC, then you have to apply for computational time either through the InSight project. So InSight is a project where you can apply for large-scale computational resources. And you have to be able to use like a big part of the whole computer. So you can't just like say I want to use one node. So your code has to be scalable. And then there are other options like they also have this AL like CC. So that's like computational challenge allocations. So there you can propose a novel research project to use the resource, and the scalability requirement is not as high, but your project has to be novel. So yeah, so you have to kind of get pre-allocations to be able to use these systems. And they also use Slurm, or at least something similar to Slurm, to dispatch jobs to available nodes and like set job priorities for different projects, etc. Does that answer your question?
Yes, it does. Thank you very much.
No problem. All right, so yeah, let's move on to the basics. So if you're new to HPC, here's the two definitions that I grabbed from the web on what HPC means, so high performance computing. Generally speaking, in my own words, HPC takes advantage of some forms of parallelism or concurrency in the algorithms to perform the computations in parallel, right? So parallel computing is certainly a big component of HPC. And I mentioned a lot about this like exascale architectures, but what does it actually mean? So HPC generally involves some forms of parallel processing, right? And HPC architectures naturally have the ability to perform parallel computations built in. In the very early days of parallel computing, we had this distributed memory architecture. So you have like one CPU connected to some memory on a single node. And then these nodes are connected through some network. And they can communicate through the network. And then later on, we have this so-called shared memory and distributed memory hybrid systems. What this means is that on a single node, you may have several parallel computing units. Right? It could be different CPUs, CPU processors, or maybe it can have a CPU processor can have many CPU cores, and they have some shared memory space. And these nodes are again connected by network. And most of the HPC architectures nowadays are hybrid. So you will have many different computing units on one compute node, and they're connected by the network. So for the distributed memory architectures, you have to have some way to send data between these different memory spaces, right? So you have a memory here, and then they're connected by the by some interconnecting fabric. And so in order to pass the data from one node to the other through some kind of interconnect, you have to have some message passing mechanism. And this is commonly done through MPI or message passing interface. But there are also alternatives like SHMEM. So this is some shared memory model for distributed memory architectures. And then PIGAs. So I'm not going to talk about this because they are used, but not as common as MPI. And so in the olden days of parallel computing, we had this like PC clusters. They're basically just like PC workstations tied together by some interconnect. And as I mentioned, nowadays, most HPC systems have a hybrid architecture, right? So you have a lot of computational cores on one node. Yeah, so in shared memory computer systems, different processors and compute cores have access to the same memory space. It makes data sharing easier because you can access the same memory, so there's no need to explicitly transfer data. However, since different processors can, in principle, write to the same memory address, you need to be sure not to overwrite the data that's already there unintentionally, right? So this is so-called race conditions. So yeah, so you want to avoid writing to the same memory address at the same time and perform the operations in the proper order. And modern CPU systems are based on shared memory architectures, including Intel Xenon CPUs and AMD CPUs, so Ryzen CPUs, etc., as well as what I just mentioned earlier, the ARM architecture is also a shared memory architecture. And parallel programming on these architectures can use MPI, even though MPI is used for distributed memory architectures. You can also use MPI to program shared memory architectures. The advantage of using MPI is that you have to tell the different MPI processes to send data explicitly. So you don't have the issue of getting into these race conditions. Or you can use OpenMP. So OpenMP, OpenACC, or pthread, etc. So these are thread-based programming models, and each thread can, in principle, use a different core. And different threads will be run within the same process. So the advantage of using these thread-based programming models is that you don't have to do data transfer explicitly, right? Because the physical memory is shared, so you can take advantage of that. I'll also talk about GPUs in a little bit later. They can also be considered as shared memory architectures by themselves, but GPU computing requires somewhat different programming models. And I'm sure Dean will also talk a little bit about this. Yeah, so after giving you this overview of different HPC architectures, you probably get a sense of the complexity of these different levels of parallelism, right? So from the system level, you have thousands of compute nodes, and each compute node, there may be tens or thousands of compute cores, depending on whether you use CPUs or CPU plus GPUs architecture on each node. And within each compute unit, you may also have the SIMD processing capabilities. And SIMD stands for single instruction, multiple data. So what this means is that in each instruction cycle, you may be able to do multiple additions, for example, or multiplications, as long as your algorithm allows that. So, for example, here I show so a very simple example of an addition of two short arrays, right? So this is array A has 8 elements and array B has 8 elements. If all I want to do is to just sum up these two arrays, or they can be arrays of arbitrary length. So A may be of like 10,000 elements, and same for B. But the operations of each element is completely independent. So in principle, if the hardware supports this SIMD capability, I can just do the addition of 8 elements, or as long as what the SIMD register supports at the same time. So naively, that would give me a factor of 8 speed up, right? Compared to just adding them element by element completely sequentially. So I give vector, I give element 8 element as an example because in modern CPUs, they often support this AVX512 SIMD instruction. And what this means is that in each instruction cycle, you may be able to do 512-bit wide vector instructions. And 512-bit translates into 8 doubles or 16 single precision numbers, right? So if A and B are single precision numbers, you can even do 16 elements at the same time. This may be a bit complicated to understand if you don't have prior knowledge. So let me pause here to see if this makes sense. If you have any questions, feel free to bring it up now. Okay. Right, so how do we program for these many levels of parallelism? So between nodes, I already mentioned that we usually use MPI to send data to and from different nodes. But on the node level, so within each node, so how do you program to take advantage of different levels of parallelism? And I'd like to introduce you to this OpenMP programming model. It's a portable programming model for shared memory architectures. So you can use OpenMP on the same node. And you may have already heard of OpenMP because it actually has been around for quite a while. It was first developed in 1997 for Fortran, and later it also supported C and C++. And even though originally it only supported shared memory parallel programming on multi-core architectures, so these are like CPU architectures, since version 4.0, it added support for also this target offloading on heterogeneous architectures such as CPU plus GPU. And the latest version is 5.2, which was released in Supercomputing 2021, so it was like November 2021. You can find the full spec specification on OpenMP's official website here. You can also get a book from Amazon if you want to have a kind of a hard copy. Now it supports several different programming and memory models, including shared memory parallelism, task parallelism, and host device heterogeneous computing. So basically GPU accelerated computing. I wanted to bring up OpenMP because for beginners, it may be an easier point for entry if you want to learn parallel programming. So OpenMP uses this fork join model for multi-threading. What this means is that the program will start with the main thread, And then if you have some tasks within your code that can be computed in parallel, then you can tell OpenMP to spawn several parallel child threads to help you do this work in parallel. And the parallel threads will rejoin once you exit the parallel region. So this is why it's called fork join model. And in the shared memory programming, all the threads have access to the same memory space. So there's no data transfer needed. But as I cautioned earlier, you need to avoid data race. So you need to make sure that different threads access the same memory in the proper order, right? And what OpenMP programming looks like is this. So it uses a set of so-called compiler directives and API function calls to support this different parallel executions. And on the left-hand side, this is a Fortran syntax. And on the right-hand side, this is C syntax or C++. So I'm a C programmer myself. So I'll focus on the C syntax. So it starts with this pound sign and then pragmas and OMP. So this is like this combination is always there for OpenMP directives. And then you can say parallel. Then it will start a parallel region. So this curly bracket, the curly brackets define the scope of the parallel region. It also provides API calls, so you can get the thread number of that particular thread and others. And to enable OpenMP, you basically give the compilers this -f OpenMP flag when you compile, or similar. So it can vary depending on the compilers you use. And if the compilers don't support OpenMP, then all these pragmas will be ignored. So how do you do parallelization with OpenMP? So when you say OMP parallel, it starts a parallel region. So you can have many different parallel threads, but it hasn't told the compiler what you want the threads to do yet. So a very useful pragma is pragma OMP parallel for, assuming you have a for loop directly after this pragma. Then the compiler will figure out how to divide the work in your for loop to assign to different OpenMP threads. So now you have the work assignment. Yeah, and you can also set the number of parallel threads through the OMP num threads environment variable in runtime, or you can set it in the code directly through the API call OMP set num threads. And there are also other commonly used constructs like reduction. So this basically reduces an array, for example, into a single number. So you can do summation using the reduction clause, or you can do minimum value search or maximum value search using reduction. Basically, reduction means you want to reduce an array, a bunch of numbers into one single number or a few single numbers, and then others. And then CMD will automatically vectorize your code if the compiler thinks your computation support can be done correctly with this CMD instruction, like I just showed earlier. Okay, so before I go into GPU computing, let me pause here and see if there are any questions regarding this CPU parallelism or OpenMP.
Hi. So you mentioned about shared and distributed interconnection models. So I was like thinking about like what is the advantage of using like share models over distributed models, like in terms of performance, like from what I have understood from a previous high performance class, like share models are in the backend implemented as distributed models. It's just that for people to create programs, it is easier to think in the share model. So I was thinking, like, what is uh, what is the advantage that's in that case?
Right. So if you're talking about just the architecture, then the distributed memory model, the distributed memory architecture, the nodes are separated, right? So the memories are actually physically separated by some distance, and you have to connect them through some fabric, like networking fabric, right? And the communication between different nodes is usually much slower than communications on the node. When you have a, excuse me, when you have a shared memory model, then the memory is much closer to the compute units. And just by physics of light, so if you want to send data from one compute node to the other, it's usually much slower. So it's also limited by the bandwidth of the network. And the on-chip memory is much faster to get to. So if you have multiple CPUs sharing a same memory, first of all, they are physically closer. So it's easier to retrieve the data that way. So I wasn't very sure if you were talking about the computation, the programming model for distributed memory systems, or you're just referring to the physical systems, or you just, because there are shared memory programming models for distributed memory systems too.
Yeah, I was referring to like the programming side model.
Oh, okay.
But yeah, I understand like how it is related in terms of how the architectures are built such that like the performance is better when CPUs like can access like the
Yes.
memory. Like yeah.
Yes. So then yes, I get it now. So exactly. So if you want to use like a shared memory programming model like SHMAM, then it is correct that it may be easier to think in terms of having a shared memory space, right, from a programming point of view. If you use, for example, MPI, you have to do a lot of fine-grained instructions to enable this message passing, right? So first you need to know the MPI rank of each node, and you need to know exactly when you want to send the data to which node. So there's a lot of like fine-grained planning involved when you want to use MPI. So in that sense, if you are more familiar with a shared memory programming model, then maybe you can use the shared memory programming model to program this internode communications as well. But yeah, you may not get as a good performance as using explicit, for example, MPI function calls. And that's generally the case. So if you want ease of programming, you may lose some performance, which is actually what I will talk about later. So I'll try to discuss this point as well.
I see. Thank you.
Yep. Any other questions before I go through GPU programming or GPU computing? Yeah, we can always come back if we have time. All right, so GPU computing. GPU stands for graphics processing units, and they have been around for a long time, at least for video games and computer graphics rendering, right, on your computers. But using GPUs for scientific computing is relatively recent. I think maybe it was started a little bit more than 10 years ago, if I remember correctly, like 2008, I think was the first time I learned about GPU computing for scientific research. So these GPUs used for scientific computing are called general purpose GPUs or GPGPUs. And yeah, they have become very important for scientific computing just because of the amount of computational power they can offer. And that's because each GPU has thousands of programming cores that can run simultaneously to perform parallel computation. So if your problem has a lot of this parallelism in it, then you can take advantage of the GPUs to offer more computational speed up. And GPU computing is the practice of using GPGPUs to accelerate scientific computing and other computationally heavy tasks. And here is just a very high level overview of what a GPU architecture looks like. Here you have some GPU memory, which is different from CPU memory. And then you have a bunch of compute cores. So this is what you see little green rectangles are just possibly one GPU compute core. So you can see there are a lot of different parallel computational units that you can use. And you can further group them into like what NVIDIA's call streaming processing units, and AMD and Intel have their different names. But basically they are like coarser grain parallel processing units if you like. And in each of these coarser grain parallel processing units, there are hundreds of parallel cores. So again, you can see like multiple levels of parallelism available in the GPU architectures as well. Yeah, that's all I wanted to say on this slide. And there are also, nowadays the GPU architectures have become more and more complicated because in addition to these multiple levels of parallelism, at the core level, they also have their own hierarchy. That's because generally lower precision floating point operations can be performed faster than, for example, double precision floating point operations. So now modern GPUs have dedicated cores to perform calculations with different floating point precisions. So so here's the data sheet that I copied from NVIDIA's website. And you can see they quote different peak performance numbers for different precisions. So they have peak P64, which is double precision. They also have what they call tensor cores, which are designed to perform matrix type operations. And then they also have FP32, which is single precision performance numbers, etc. And so they have basically dedicated cores to perform this different precision calculations with different peak performance numbers. So if you want to take advantage of all these different capabilities, then you also need to support it in your programs. Now, I keep saying peak performance. And when we talk about exascale computing, we actually mean sustained performance of exaflops. So you can easily find the peak performance information from the compute hardware data sheets, like the one I just showed here, right? So these are all peak performance numbers. And you can also figure out the peak performance numbers of your computers, your laptop or workstations. And to come up with these peak performance blobs, what you need to do is just do a simple calculation. So here's an exercise that you can do at home. So you can calculate like the peak performance of your laptop or desktop. And the performance in gigaflops, if you're doing double precision peak flops calculations, you can do this. So you can multiply the CPU speed in gigahertz. So this you can find out by just looking at your system details or run Linux command like ls CPU. Multiply it by the number of CPU cores on your system, and then multiply it by CPU instruction per cycle. And then multiply SIMD operations per instruction, and multiply it again by number of CPUs. So why do I separate CPU instruction per cycle from SIMD operations per instruction? That's because most CPUs nowadays can perform fuse multiply add in one cycle. So if you have like A plus C times D, then it's technically two operations, but you can fuse them into do the computation in one CPU cycle. And SIMD operations per instruction depend on what your hardware supports. So it can be SSE or AVX or AVX 512. And all this information can be found out through some Linux command like lscpu. Anyway, so this is your homework for today. So it's easy to find out the theoretical peak performance, but the sustained performance, so that's the actual performance you will get, depends on a lot of other factors. In particular, for GPU computing, it depends on data locality. So where your data are stored, and do you reuse your data? I didn't talk about this, but even on the GPUs, there are like different hierarchies of the memory, hierarchies of where your data may reside. Even though from programming's point of view, you load the data from CPU to the GPU into the GPU memory, but there are also different levels of GPU memories like L2 cache, shared memory, etc. Yeah, it also depends on how many floating point operations can you perform with a given amount of data, because the more operations you can perform on a fixed amount of data, the better performance you'll get, right? So again, data transfer is the bottleneck here. So if you have to get data frequently from CPU to GPU or from the disk to CPU and then to GPU, then you're not going to get very good performance, because despite the number of parallel cores available on the GPUs. And then there's also this notion of occupancy. So how well can your algorithm saturate the cores and threads? So these two are kind of related. And then again, multi-node performance will also depend on the communication overhead, right? Sending, receiving data to and from other nodes. What's the difference between CPU and GPU? So CPUs are generally very fast, so in terms of the clock speeds, but they only have a limited number of cores, maybe 64 cores. I think the newer ones may have like 128 cores. And you can use one thread per core, so maybe you can use like around 100 threads per CPU. But they do come with very large main memory. So you can have 512 gigabytes of CPU memory easily. And the CPUs have very fast caches, but the cache sizes are very small. And the cons is that the CPU memory usually have very low bandwidth because usually they are connected through PCIe bus, and the bandwidth there is about 12 gigabytes per second. And the advantages of GPUs are they are very power efficient. So they have they can offer very high performance with relatively low power consumption. And each GPU core will have a much slower clock. So each core can't perform as fast as one CPU core, but we have so many more of them, right? So you need a lot of parallelism to take advantage of GPUs. And GPUs have very high memory bandwidth because now they have these fast interconnects. For example, NVIDIA has this NVLink connect. And AMD and Intel have something similar, though named differently. And GPUs usually have smaller memory capacities. The latest NVIDIA GPUs on the market, A100, have, I think, up to 80 gigabytes memory per GPU. Yeah, so GPUs are now very popular among the supercomputers. It's because of the amount of computational power they can offer, and also because of their low power consumption. So here are just a few of them. And notably, two of the top three supercomputers nowadays are powered by AMD GPUs. So before, they were all powered by NVIDIA GPUs. So, but of course, NVIDIA GPU-powered supercomputers are still very common. Right. Yeah, so and Intel also has its own GPUs, although they haven't officially released any for the HPC systems. And how do you program to use these GPUs? So at present, GPUs are used as accelerators to the host CPUs. So the CPU will launch the program and dispatch the work to either the CPU or the GPU. Data will first need to be loaded to the CPU from storage or from some initialization. Of course, you can also use newer technologies like GPU Direct that can load data directly from storage to the GPU memory. And to perform GPU computation, you need to make sure data is available on the GPU memory. And there are two ways to do this. You can do explicit data management. So you use some API calls to send data from CPU memory to GPU memory. Or you can use the new unified shared memory or managed memory model. So nowadays, the GPUs will all support this, although you may pay a price of some performance penalty. So I'll try to go over this very quickly in the next few minutes. Yeah, so in terms of the parallel components, the parallel computing part, there are several GPU programming models that you can use. The first one is OpenCL. This was used in the early days of GPU computing, and it's an open standard. It's an open standard for programming heterogeneous systems. So you can write your code in OpenCL, and then you can run it across different GPU architectures. The disadvantage of using OpenCL is that this is a fairly low-level programming language. So you will need to write in fairly low level instructions like manipulations. You need to tell the compiler exactly what you need to do. And then came CUDA, which is NVIDIA's GPU programming API, and it has a C++ like interface, so it's relatively easy to use. But the disadvantage is that it only supports NVIDIA GPUs. It wasn't a problem before because basically NVIDIA GPUs were the only ones available. But nowadays, since we also have AMD Intel GPUs, you need to think about the portability issue. And so HIP was AMD's answer to CUDA, and it's basically kind of a wrapper. So it supports both NVIDIA and AMD GPUs. And it's also adding support for CPUs, like thread level programming for multi-cores. And then there are other kind of third-party high-level portable programming models, such as OpenMP, OpenACC. So they're both directive-based programming model. So I showed some very simple examples of OpenMP. OpenACC is similar. So instead of saying Pragma OMP, you say Pragma ACC, and then a set of directives that OpenACC supports. And then there are also these so-called portability layers, like Cocos, Raja. So these are all DOE supported programming models. Cocos and Raja are both C++ abstraction layers, and SYCL is actually an open standard, and it's also designed for C++. Yeah, I won't have time to go through all the details, but if you're interested, you can, I think, easily look them up. In my view, they are very interesting, so I would encourage you to do that. Okay, so I want to just give you some glimpse of what GPU programming looks like. As I mentioned, there are two major components of GPU programming, right? So first, you need to make sure that data are available on the GPU. And then you also need to do this work sharing handling, right? So you need to let the compiler know how you want to share the parallel work. A simple CUDA-C example is a simple array multiplication. And first, we need to create a device function that tells the compiler that this will run on the GPU. So you use this global __ global keyword. Then you need to make sure the data needed for computation on the device are available. And to do that, you need to allocate device memories. So like these dev variables indicate that the variables are supposed to be device variables. And then you need to copy the data from host to device or from device to host after you've done your computation. And then you need to tell the compiler what you want to parallelize, right? So you want to parallelize this multiplication function. And this is you want to do this through this number of threads, etc. So it looks fairly complicated. A unified memory basically gives you a way to simplify memory management. You still need to do the work assignment using this syntax, but instead of allocating CPU memory and then allocating GPU memory separately and then doing the memory transfer explicitly, in CUDA, you can use this CUDA managed API to indicate that now the pointers X, Y, and out are managed memory pointer. So managed memory basically means the CPU and GPU will have a shared memory space, even though the physical memories are still distinct. The runtime will handle when and how to transfer the memory from CPU to GPU or from GPU to CPU automatically, depending on what you when you need the data. So the catch is that there may be some performance penalty. So as I said earlier, ease of programming usually comes with the cost of lower performance. But all the GPU vendors have been improving the low-level software stack to reduce this performance penalty. So it's actually quite impressive how well unified shared memory can do nowadays compared to just the manually managed memory. Okay, so let me see. Okay, I am very behind on the schedule. So do you have any questions up to this point? Okay, I want to quickly go over OpenMP for GPU computing because this is very interesting and you can try it out fairly easily afterwards. So I mentioned OpenMP for CPU, like multi-threading, but you can also use OpenMP for GPU computing. And here's an example. So this is just a simple array multiplication, right? Actually, just a multiplication of two numbers and assigning the results to an array. So if you want to do multi-threading, you would just say pragma OMP parallel 4 without the rest, right? So that's what the example I showed earlier for GPU, for CPU was like. In order to do GPU computing, you need to use this target keyword, and target indicates the code block below will be executed on a target device that you will define when you compile, right? So here's an example with like the G++ compiler that it will set OMP targets to be NVIDIA's particular GPU. So, and then you set a number of, you will say teams. Teams indicates that there will be a league of teams doing the work. So this would usually be mapped to, for example, SMPs on NVIDIA GPUs, so streaming multiprocessors. And then distribute means the teams will share the work. If you don't distribute, you will have a bunch of teams, but they may be all doing the same work. Parallel, that just means the work will be shared by parallel threads. So now you can assign the work further into different like GPU cores. And so how teams distribute parallel these clauses map to the actual GPU architectures also depends on the compiler, but more or less what I just said should be the case. And then to handle the data movement from CPU to GPU, in OpenMP, you use this map clause. So you can say map to, so XY means you want to copy the values of XY to the GPU memory and store the data in XY copy on the GPU memory. And from is copying back from the GPU to the CPU. Yeah, so I'm not going to go through this, but yeah, basically you can find kind of a one-to-one correspondence between OpenMP and CUDA. And this is data copying. So an OpenMP use map and CUDA use CUDA mem copy or CUDA malloc managed. And OpenMP also supports managed memory. which I'm not going to talk about, but it's very easy. You just use like requires unified shared memory. So it's kind of fun. Yeah, and OpenMP, it's a, yeah, why use OpenMP? So I mentioned portability, right? So OpenMP is a community standard that has support from basically all the GPU vendors, AMD, Intel, NVIDIA. They're all on the OpenMP committee. And so in principle, it's a very portable programming model. And directives such as those from OpenMP are very easy to add to existing code. So if you have some code that you want to port to the GPUs, you can just add the OpenMP pragmas. However, performance may not match the architecture-specific implementations, such as using CUDA or HIP. But a lot depends on the compilers, right? So, and the compiler implementations have improved dramatically in the last few years. So I would not be surprised if in the future, OpenMP performance can actually match the architecture-specific implementations. And also, the same code can run on both the CPU and the GPUs because you can set the target to be just your CPU. And there are other GPU programming models that I mentioned a little bit earlier. So HIP, OpenACC, Cocos, SYCL. This is what Intel advocates. So Intel has their DPC++ compiler to support SYCL programming. Yeah, if you use Python, you can use CuPy. So the CuPy is also very interesting, but I don't have time to get into that today. But just to let you know that if you use NumPy in your code, it's fairly easy to convert your Python code into CuPy. And CuPy supports both NVIDIA and AMD GPUs right now. Right, so I don't know if I have time to go through the case studies. But let me just pause here and just see if there are any questions up to this point. Okay. Then maybe let me just go through some of the interesting results. So yeah, my background is in Lattice QCD, right? So I'm interested in like how to use exascale computers for Lattice QCD. But right now I'm also working with some experimentalists, colleagues from like Atlas and Dune, to see how we can transform the experimental high energy physics software to use the exascale computers. So my understanding is that you all have very different backgrounds. So let me just give you a very high level introduction to what experimental high energy physics and Lattice QCD have in common. So they both need very significant computational power. And traditionally, experimental high energy physics relies on high throughput computing that basically runs embarrassingly parallel jobs on thousands of CPU cores to process independent events, right? So the high throughput computing basically just run on many different cores, and each core will run more or less the same computation, but with different input. And Lattice QCD relies on more tightly coupled HPC clusters, such as Summit and Perlmutter. And that's because we have very large high-dimensional parameter space to simulate. And it also takes years of running to produce meaningful physical results. So exascale computing may significantly boost the computational power for a GPU. But as I emphasized a lot of effort needs to be put in to basically get the most benefits of the exascale computers. So Lattice QCD is a numerical framework to simulate the strong interactions between quarks and gluons. I saw some of the lectures in the next 2 weeks, and I think you will learn more about this. Basically, discretize continuous 4-dimensional space-time, and we should kind of we kind of assign quarks to the lattice sites and the gluons to be the links between the sites. And we use lattice QCD to study a lot of interesting physics, such as internal structures of protons and pions, etc. And we use lattice QCD simulations to look for hints of new physics. And it's based on Markov chain multicolor simulations. And another key ingredient of lattice QCD simulations is sparse matrix inversions. So there are basically 4 steps of lattice QCD simulations. The first one is gauge ensemble generation. So in this step, we use Markov chain multicolor techniques to generate ensembles of the gauge fields according to the Euclidean QCD path integral. And the second step is to calculate the quark propagators on these gauge ensembles. And in this step, this is where the sparse matrix solver comes into play. So we basically solve this mx equal to b equation, where m is the Dirac matrix and b is the source vector for the quark propagator, and x is the solution we want. And m is very, very large, so it can be like 10 to the 10th by 10 to the 10th in the modern lattice QCD simulations. So it's very computationally expensive. And then we do the weak contractions to get the correlation functions that we want to extract the physical observables. And then the last step is data analysis also, of course. So we do fittings to get, for example, the particle masses or form factors, etc., that are of interest to us. Okay, I'm not going to go through the numerical algorithms for lattice QCD, but this is the partition function for our path integral. So in the Euclidean space, and we'll introduce this pseudo fermion fields to enable us to do numerical simulations. Because usually, if you don't do this, then we have to calculate a determinant, which is very numerically expensive and impossible with the current computational resources we have. So we trade calculation of determinant with the calculation of matrix inversions, which can be done iteratively to the precisions we need. Yeah, so this is the Dirac matrix that I mentioned. And so in QCD, we know exactly what this matrix vector multiplication will look like. So we don't actually store the matrices, right? So we just store the input gauge fields. And these gamma matrices are already known and fixed. So when we say d/ operator, we just mean this calculation. And this is actually not very good for supercomputers in the sense that we have very low arithmetic intensity, which means we can only do certain amount of floating point, a very low amount of floating point operations with a given data, like in terms of flops per byte. So it's like around 2 flops per byte. But apparently lattice QCD is not the worst in terms of the arithmetic intensity. But what this means is that we are memory bandwidth bound. So we want to avoid copying data back and forth as much as possible. So we want to do as much computation with the amount of data we have as possible. Yes, and in order to get physical results, we need to do several extrapolations. So we need to extract results to the extrapolate the results to the continuum continuum limit because we discretize our space-time, right? So we have this finite lattice spacing. In order to do the continuum extrapolation, we need to do simulations at different lattice spacings. And so that's one additional cost for the continuum limit extrapolation. Another one is actually from the algorithm side. So because the typical correlation length goes as 1/a, as we get closer and closer to the continuum limit, it becomes harder for us to generate independent gate configurations. And this is what we call the critical slowing down problem. So we either need to run the simulations longer or we need better simulation algorithms. So when we use the hybrid multi-color simulations. So there is actually a dedicated ECP activities, Exascale Computing project activity for lattice QCD to investigate better HNC algorithms to conquer this critical slowing down problem. And then we also need to extrapolate to the physical quark mass. In the olden days, we were not able to do simulations at the physical quark mass. That's because the condition number of the Dirac matrix is proportional to 1/m. So if m is small, the condition number is very large, which means the iterative solvers will need many iterations to converge. But now we can actually simulate directly at a physical quark mass. But that means the computation is very expensive. It's much more expensive than simulating an unphysically heavy quark mass. And then I saw a lecture title about noise to signal ratio. So as we go to lighter and lighter quark masses, the noise to signal ratio will also grow exponentially. So that means we need more simulations to reduce or to get the statistical error we want. Yeah, so all these contribute to the growing computational demands. But of course, there are also challenges presented by the machines available to us. So how do we make full use of the flops provided? And similarly for the experiments, right? So we have all these different architectures that we need to use. Yeah, so software considerations, we want to be able to write portable software so that the same code can run on different exascale architectures. And we want to choose data structures and layouts that are amenable to GPU computing. And for the performance portability part, we want to consider which programming model we use. And there's no one size fits all solution. So you kind of have to decide for yourself which programming model is the best for us. So we may have to try a few of them and see if it works, because every problem is different. And this is actually a major part of the Exascale Computing project. So we want to look into different programming models and see which one is the most suitable for lattice QCD and other applications. So in terms of lattice QCD, we are part of the Exascale application development project, and it is a collaborative effort between 4 DOE labs: Argonne, Brookhaven, Fermi Lab, and Jefferson Lab, and also 7 university partners here. So many institutions are involved. And roughly speaking, the lattice QCD Exascale computing project are grouped into 4 activities. So if you remember the 4 computational steps for lattice QCD I showed earlier, so there's a group working on workflow. So basically the contractions. How do you do the correlation function calculations efficiently? And then there's a group tackling this critical slowing down issue as we go to finite and finite lattice spacing. Also a group working on linear solvers And I am mainly working on the data parallel API part of the project, just to explore different program models and see how we can best program for different exascale computers. Okay. Right, so Lattice QCD software suite is very complicated. So we have the application layer, which consists of 4 main components. So each software suite focuses on a different thing, but they all rely on some performance critical libraries like CUDA or Grid, and then underneath, or within CUDA and Grid, there are also different choices for the programming model like CUDA, HIP, SQL, DPC, OpenMP, etc. And we're exploring all these solutions. There's also Cocos, which I'm not listing here, and with the goal of being able to run on all these different GPU architectures. I don't think I have time to go through all these details, but just to flip through them. So they are more or less related to the basics I presented earlier. Just an actual case study to show you that OpenMP can achieve the similar performance as CUDA, at least in this simple benchmark. And then some work that I've done with the experimental high energy physics communities. So we are basically investigating different portable parallelization strategies. So we're looking at Cocos, SQL, and OpenMP in particular right now, with the possibility of looking into other solutions as well. So the goal is to enable portable programming for these different experiments. So we're working with Atlas, Dune, CMX, etc. And their code so far doesn't have GPU computing support, or doesn't have much GPU computing support. So we're trying to figure out what the best way is to get their code to run on the GPUs with portability in mind. Yep. Okay. So just some results like Cocos. Again, it can achieve more or less the same performance as low-level architecture-specific programming models. We also look into SQL, similar conclusion. So there are some overheads associated with using these high-level portable programming models. But I think the trade-off is worth it since you're getting the portability from using these high-level models. So this is another example with Dune's software. So we've done Cocos and are looking at OpenMP and SQL as well. Yeah, so let me just summarize here. So yep, we are in the exascale era, and we have a lot of opportunities to advance computational research. However, care has to be given to software implementations as well as algorithm considerations to efficiently use the exascale computers. Programming models that can offer portable performance across different architectures may help reduce the burden of programming for exascale computers. So they are definitely worth looking into. And yep, I think that's it. With that, I will stop and see if there are any questions.
Dr. Lin, I'd have a question for you. It's kind of two parts.
Mm-hmm.
So You normally hear about when we're talking about the exascale era about the actual computational resources that we require. And I don't hear as much about the actual storage and data analysis portion and the needs. So you're generating terabytes of data and you need to be able to process this. And you mentioned that you're working on this processing API. So I'd be curious to hear both your take on the relative needs between computing versus the analysis and storage, as well as kind of a little bit more about what you're doing on the on that side on the project.
Excellent question. Yes, actually, that's a lot of people are realizing that because with the new experiments coming online, we're expecting a lot more data, right? So I think that has something to do with the history of HPC. Traditionally, I think HPC is used mostly for like numerical simulations, right? So scientific computing, you just simulate. You do also generate data, but the amount of data that you generate from simulations is not usually that big, or you do some sort of pre-processing or post-processing to reduce the data that you need to store on storage. But now I think a lot more of these experimental programs may look into using HPCs as their computational tool. And indeed, storage is an issue. So I don't have much personal experience in storage-related research just because of, I guess that's just my limitation. My focus is more on the processing side of the things. But so in terms of storage, you want to think about the amount of storage available, right? So that is not a big issue. So you can have petabytes of storage or exabytes of storage. The issue is loading the data into the processing unit, and that's a challenge. So I don't think exascale computers are going to be very efficient for all the different processing needs. So you may have to pick and choose to see if your data analysis workflows will be able to take advantage of all these GPUs. Yeah, I don't know if I answer your question because I don't really know the answer. So I think that is a challenge, and you probably have to decide case by case. But of course, there are newer technologies available, right? So like the GPU Direct I mentioned may be able to help a little bit. So if you can bypass one step in transferring your data from storage to the processing units. I don't know if I partially answered your question or not.
Yeah, that's fine. Just knowing it's still an active area of interest is excellent in its own right. So thank you.
Yeah, there's definitely interest, and there's this awareness of the storage being a potential issue. And also it's because of my limitations. It's a very biased presentation for exascale computing because yeah, I just talk more about what I know most.
Alrighty then. Thank you very much, Dr. Lin. We really appreciate your talk.
My pleasure. Thank you for being here.